Welcome you to today's session. Today we will look into one of the major important topic, what do you call it as an oscillator. So we would like to go by this particular topic, oscillator topic. So first of all, let's try to have a little bit of clarity on what is this amplifiers, oscillators, right? These two come under the broad category of feedback based circuit. Feedback based circuit means what I'm trying to do, I have a system, I tap the output of that particular system and then feed a part of that output as an input apart from the primary input which I have. So now the output depends upon the present input and the feedback which it is given to given in addition to this present input or the primary input which you are having in. So some cases it may be like aiding the primary input, that is the feedback which you give in, may be aiding the primary input which you are giving in, or sometimes it may be opposing the primary input which you are giving in, right? So it's something like a corrective mechanism which is being required to stabilize my system or produce a constant output for my system. So what I'm trying to do, I take a sample of my output, which you call it as a feedback fraction, and then feed as input for the present input and make sure my system remains stable. Now, this two category, amplifier and oscillator, comes under the way this feedback fraction is going to act with the primary input. If it is going to aid this, means if it is going to add towards the primary input, then I classify that type of feedback as positive feedback, and that has been used in the oscillators. If I give feedback which is going to oppose my present input or the primary input, then I call that as negative feedback. Negative feedback. This negative feedback is being used in the amplifier. So now what we understand, basically the types of circuit wherein the output has been sampled out and it has been fed as an input which aid or oppose the present input, we call them as feedback based circuits. In fact, these type of feedback circuits is being used widely for most of the control networks and amplifiers, designing amplifiers, oscillators, all this, right? So as I said, you can classify them into two broad classification, this feedback, one to be under negative feedback, other one to be under positive feedback. The point is feeding a portion of your output signal back to the input circuit. This we call it as a feedback. The effect results in dependence between output and input, which means the output changes in accordance with the primary input as well as the feedback fraction which you are trying to give in. So what is the thing which you are going to get out of it? It's going to give me an effective control on the output or working of that following system. Now the question is, I would have said, like we are going to use negative feedback to the amplifier. This is a little bit conflicting, means amplifier, the whole purpose of the amplifier is to amplify a signal, means in order to increase the amplitude of a signal, we go for amplification. Under that case, I also said we are going to give negative feedback to the amplifiers, which mean a negative feedback will reduce the effective input that has been provided to that. Okay, now here comes the question, why am I supposed to go with negative feedback for the amplifiers? So what you could see, this negative feedback can also be called as degenerative feedback. In fact, it is not going to add it up, rather it is going to decrease or it is going to oppose the present input. In spite of this, we use negative feedback for some of the following reasons. Okay, Let it be like this. In general, the feedback, the parameters which has been fed back can be voltage or current. Or what I'm trying to say, the feedback, what you can do is you can take the output voltage and give the feedback as voltage towards my primary input or the input given for that particular system. So this is my feedback network. So what voltage is sampled here, voltage is fed over here. Otherwise, I may sample a current here and feed this as a current. Next, I can sample a voltage here and then feed as a current. I can sample a current here, feed as a voltage. So I can come across with 4 different combination, right? By using these 2 variables, that is the sample variable is either a voltage or a current. Okay, so now we could see either it could be voltage feedback, current feedback, current voltage feedback, voltage current feedback. So you can come across these 4 different circuitry in order to feedback. Okay, the next variety. You can have in this way also. Say, suppose this is my system, this is your input, and here you are sampling your output, and this is your feedback network. And now the way by which it has been sampled, right? So you can do it in series or in parallel. So tap the output in series, give it in series with the present input. So series feedback, parallel feedback, serial parallel feedback, parallel serial feedback. The point is the way you tap the output and the way you feed in the feedback fraction to the present input. Based upon that topology, you can classify them as serial, parallel, serial, parallel. So again, you can have 4 different combinations. But basically, of course, both are almost the same. This is the parameter which you sample. It is the way you sample or the topology by which you sample it. Got it? Right. Usually, the current will always be in series. Voltage will always be in parallel. So wherever I mention series, it refers current. Wherever I mention voltage, it's going to be in parallel. So when I say parallel, it means voltage feedback. When I say serial parallel, then it means current to voltage feedback, voltage to current feedback, current feedback. So in nutshell, you can have, based upon the parameter and the topology by which it is connected, you can have a feedback, voltage feedback amplifier, current feedback amplifier, voltage current, that is voltage to current feedback amplifier, current to voltage feedback amplifier. All this 4 combination could take place. Simple. So in a negative feedback, the feedback energy means the signal what you are going to sample might be current or voltage. And it is out of phase with the input signal that thus it opposes it. Basically, this is our idea. So whenever I say negative feedback, it is not going to aid it, rather it is going to oppose it, means it is going to be in out of phase. Now, we said it is going to be an out of phase. When I give a negative feedback, what else will be the consequences? Definitely, it reduces the gain of the amplifier. Okay. Now, this seems to be a disadvantage because your intention is to amplify a signal. Gain should be high. Now, when I give a negative feedback, it says that it will reduces the gain. Now, the next question which comes in is why should I then go for a negative feedback? Correct. If I give a negative feedback, definitely it is going to reduce the gain. But in addition, it's going to give me some extra features. What are they? It reduces distortions, noise, and instability. These are some of the important things which system need to possess or desirable property that a system need to possess. It should be free from distortion. It should be free from noise. It should be having stability to be high, or the instability should be reduced. Definitely, they are our desirable future for a system design. Though my gain reduces, I get these things as my advantages. That's the reason we use negative feedback for the amplifiers. Right. One more important thing is it increases the bandwidth. What do you mean by bandwidth? The range of frequency over which the gain remains constant. The range of input frequency over which the gain of the circuit remain constant. That range is called as the bandwidth. Now what it says is the bandwidth increase. So what am I going to get out of it? With the bandwidth increase, then what we understand is large amount of input signal over a wide range of frequency can be amplified. That's the biggest point. So what I want is always a desirable system need to have a high bandwidth. Okay. Beyond this, it improves the input output impedances. What do you mean by this? Typically, when you take a system, it has its input impedance, it has its output impedance. Basically, it's resistive power, right? It could be a resistance, it could be an inductance, inductive reactance, or it could be capacitive reactance, or the combination of both, which will be called as an impedance. Okay. What are the desirable property of this? Generally, a system need to have very high input impedance and very low output impedance. Strictly speaking, the ideal case is you need to have infinite input impedance and zero output impedance. Why it is so? The reason is very simple. If you have infinite input impedance, what does that mean is it will load my source, or it will take only very less amount of energy from the source. This is what actually we need it. Right. Then if you keep output impedance to be very high, then it will not load the output. Means it will not take away some of the output because of its output impedance. Since the output impedance zero, the total output that has been generated out of the system will be given as an output for the load. So for an ideal system, you need to have very high input impedance, very low output impedance. So these are the very important point. And as far negative feedback is concerned, it does that. It improves the input and output impedances. So due to this advantages, this negative feedback is quite often being used in all amplifiers. Okay, a simple example what we give here is, look at here. So this is my amplifier. Common emitter amplifier, which is a very basic amplifier which we use in the common emitter configuration of the BJT, or even if you take MOSFET, common source amplifier, they produce a phase shift of 180-degree phase shift. So what I understand, it amplifies the signal and provide a phase shift. Look at here, this is my input signal. This signal is amplified, but out of phase, right? Okay. Now, this is a feedback circuitry which is sampling the output and feeding that as an input as in addition to the present input, which means this feedback fraction is going to oppose this input, right? So in this way, we said it is a negative feedback system. So for all our amplifiers, we said it is going to be a negative feedback amplifiers. Next. Positive feedback. What is this positive feedback? Now again, let's see the feedback fraction. It is going to be in phase. The keyword is in phase with the input. And it is going to aid. Positive feedback increases the gain of an amplifier, right? And it at the same time, it increases distortion, noise, and instability. Because of this disadvantage, positive feedback is never being employed in amplifiers, but it is being used in oscillators. The point is only this one. Oh, there is one student attending. Sorry.
Sir, I just saw a message on the WhatsApp group saying that there was a class being held right now. I have no idea what this class is for. Is this like an extra class or?
No, I'm just recording it. You need not,
Oh,
if you have, you can go ahead. But the same thing will be passed on to you.
sorry, this is for the for referencing.
Yes, yes, yes. So this is something
Okay.
like an extra class which we planned. If you want, you can stay. Else, I will be pausing this video so that you can use it.
Okay, thank you. I think I'll stay.
Okay, okay. So now the point is, um, like this positive amplifiers, positive feedback. Why do we need it? See, we already said the feedback which we are going to give in, it's going to aid it, which means it is going to increase the amplitude of my input signal. So naturally, it is going to increase the overall gain. But the problem is, it's like a cumulative action which keeps on adding it up. The feedback keeps on adding it up. It keeps on increasing, increasing, increasing. It goes without a control. If you don't have an appropriate control, then every noise which is present nearby that get amplified, and you'll be having a miserable sound at the output receiving side. So thereby, it increases the distortion, it increases the noise, it increases the instability. Now, the biggest challenge is when you want to create an oscillation. What do you mean by oscillation? Oscillation is generating an output signal with desired frequency and sustained oscillation. See, like I can have something like this. You can have an output. It's a damping oscillation. Means at one point it has some frequency, at the other point it has some other frequency. The amplitude keep on decreasing. At one point it dies out, or it could be like this also, right? This is also an oscillation. But when we say oscillator, we define an oscillator. An oscillator is a circuit which provides a desired output signal with a particular frequency, and it need to have a sustained oscillation with stability. Means, so when I say, see, this is a sine wave oscillator, what does that mean is it is going to generate a sine wave of a particular frequency. So without any input, that's more important. This is the only circuit which generates an output without input. Without input, I need not give any input. Still it will produce my oscillation with a particular frequency. And it provide me a sustained, it will not die out. So basically a circuit which produces a sustained oscillation with a particular frequency. That circuit we call it as an oscillator. Now, the next question which comes to our mind is, how come a circuit capable of producing an output without any input? The point is very simple. Now, let's consider this to be an oscillator. This is my input. This is my output. I sample this through a feedback fraction beta and then give that as an input for my input signal. Now, what I'm saying, even if you don't give any input, the external noise which is present around that, you could see there could be many noise. It could be device noise, it could be environmental noise. Like this, you may have n number of noise which is having its own frequency. Now, the beauty of that is this circuit will pick up one particular frequency which satisfies certain condition and start generating the output to that particular frequency, and that will be its oscillating frequency. In that context only, I said you will not be having any input. Strictly speaking, it doesn't have any input. For some circuit, what we will do is we will give a simple to start up like this. So something like engine start, we need to kickstart, no, like that. To kickstart it, we will give a trigger pulse. After that, we will leave that. That trigger pulse will evolve around this loop and it start producing output signal. That's the beauty of this feedback network, positive feedback network. So what you could see, look at here. You have an amplifier. This amplifier produce 180-degree out of phase. Now you have tapped the output out of that. Now important thing is this is in out of phase with this input and output. It is 180-degree out of phase. That is okay for an amplifier. You can directly feed in. But for a positive feedback, this output should be in phase with the input, which means either it should be 0-degree or it should be 360-degree. It should not be 180-degree. So what I try to do, take this 180, add one more 180 to this. Either you add it or you subtract it, thereby it becomes either 0 or 360, which means this feedback will be in phase with that of your input. That's why this becomes a positive feedback. So the main condition is giving a positive feedback, which means my feedback is in phase with respect to input. That's why we call it as a positive feedback. So here my important point is, apart from the feedback fraction what to sample at their output, you need to have a circuit which can introduce 180-degree, because this 180 is going to add up with that 180, thereby produce 360. Or it could even subtract 180, thereby it can produce 0-degree. Got it? So, so we will stop here. We will look one more video. I will frame one more video, and the second part of that video will come in the next hour. Thank you.